So I'm going to talk largely about Beam today. You may have heard the previous session from Google. So this is a continuation on that. Just to compensate, at the Apache Beam meetup in Canary Wharf in October, I will talk about Flink. So that should compensate for me talking about Beam here today. The background here is that we tried to emulate a pricing engine with Apache Beam. I won't stick to this slide. This is general gumph. But essentially, a pricing engine involves sourcing a bunch of trade data, and the trade data is associated with its market data. There is a workflow process that defines a set of actions you have to do on a trade in order to price it. Typically, it is introspecting the trade, working out the relevant market data for that trade, and then making that C++ call that does the pricing job. Traditionally, this is done through a distribution engine using data synapse is the normal tool that people have used over the last 20, 30 years in this field. It is a TIBCO product. It is fairly robust. It manages through grid brokers and grid directors, manages task distribution and things like that. It is very much, as you can imagine, a batch-based process. When the batch is complete, the results are dumped to either a cache or a disk, and then it's read into a database. So we started to look at Google Dataflow about towards the end of 2016, 2017, when it still was Dataflow 1.9. And the question being asked was, will Dataflow do the same thing? Will it act as a risk engine? And that is the question we set out to answer. The answer at the end of the day was yes, it does work as a risk engine, but there are caveats associated with it, and we'll come to that shortly. As we progressed through this, Dataflow towards July last year became Apache Beam. The official release came out, and we switched to Apache Beam with Google Dataflow being the runner. Now, so people who attended the previous talk, there was a slight bit of introduction to what Beam is. Essentially, it's a functional programming paradigm. There is a do function, which you can. So essentially, a do function has an immutable input and it emits an immutable output. People familiar with Flink would know this. And it's only the do function that is allowed to mutate that data from the input to the output. You can chain a series of do functions which produces your DAG or your directed acyclic graph. And that is what gets distributed across the workers that you want to farm it out, the DAG to. The concept of a parallel do is essentially make sure that these functions get parallelly executed on the workers. So we went up to 20,000 workers on Google Dataflow. So that is the level of parallelism that was tried out in that context. The DAG ensures, obviously, that a function, if there is a dependency, or for example, in this case, function D is a group by where it is grouping the results of B and C together, it makes sure that everything in B and C has been executed before your group by does. So one thing you notice in Google Dataflow is if you do not have a group by function like function D, Dataflow does this thing called fusion, where it fuses a whole bunch of do functions into the same worker process. So it introspects your DAG and does that fusion piece. It is quite impressive in the way it manages to get that fusion working, and the throughput is pretty phenomenal. This is more of the same. In our particular case, we were making a external C++ call, which is the trade and market data is being transferred to a C++ process. The problem is that when you do this, when there is a memory violation in the C++ process, and there is a segmentation fault, a signal 11, it takes the container down with it. So if it's a JVM, the JVM will crash as a result of that. If you're running Dataflow in batch mode, Dataflow will try 4 times, and then the whole batch will be abandoned. If you're trying it in streaming mode, Dataflow will keep repeating the process ad infinitum, and your process will simply keep crashing forever until you manually go and intervene and kill the streaming job. In both cases, it's an undesirable side effect, because if you have spent half an hour pricing 2 million trades and the last trade causes a crash, you have just lost all your processing time. So the question we asked was, I mean, this was one of the problems with running an external process call through Beam. So the suggestion that was made to us is that you fork at that point from Java into the external process. You can exchange the data between C++ and Java we first did that through streams. We were exchanging data between Java and C++ by streaming data out to the C++ process. We quickly abandoned that because the problem with the problem that happens in that case is when you are listening to the output from the C++ process, if the C++ or the C process has used external libraries, there is a lot of noise, which there may be logs coming from the external library, which pollute the result stream that you're expecting from C++. So you don't quite really know when your results have been completed and when the rest of it is just chatter. In order to avoid that, we started to write within the container. We started to write the trade and market data to the /temp area of the container. Typically in protobuf, the C++ would read the data in. It would write the results output back to /temp and will signal back to the container saying its job is done, and the worker process carries on from that point onwards. This is a gRPC call between that you make to the external C++ process when you fork it out. It costs about 6 milliseconds to fork this process out, especially in Google Dataflow. And the amount of overhead, we were very skeptical about this because we thought it would add a lot of overhead to the pricing process. Contrary to what we thought, it actually didn't add that much. On a 3,000 worker process for 2 million interest rate swaps, it went from I think it went from something like 45 minutes to 46 and something minutes, or 45 and something minutes. It actually, if you look at the total time it took on the whole job, it was relatively cheap to make this out of process call. The obvious advantages of using protobufs, is what the rest of the slides are all about, which I'm not going to. Everyone knows these obvious things. The only caveat is I discovered that you cannot use protobufs within the Python process because the whole thing has been rewritten in Python Beam rather than Java Beam. And with Python, there is a pickling problem in Python. So you have to actually move JSON objects around in Python and then convert it to protobuf at the point when you communicate with your C++ process. But apart from that, there is no difference. The Flink piece comes in. So we ran this in Google Dataflow. The Flink piece comes in terms of us not wanting to do this in Google Cloud. We wanted to do this inside the premise of the institution that this was being tried out on. And we wanted to benchmark the Beam process running on Flink versus the Beam process running on Dataflow. And we were expecting the Flink process to be beaten quite badly by Google Dataflow. What we discovered was quite surprising, quite gratifying. There are a few things about writing Beam jobs. So inside the institution, the repository was MongoDB, and the output was going to disk. In Google Cloud, the repository was Bigtable, and the output was going to GCS. Now, there is a technique where you can make sure that your pipeline code does not directly refer to MongoDB or to Bigtable, so that you can actually take the pipeline and migrate it from the job running on Flink directly to the job running on Dataflow. You can, just through the pipeline options, inject the source and the sinks that the pipeline has to communicate with. So this means that the CI/CD pipeline that you develop inside your premise can then simply translate the deployment process to Google Cloud or to AWS or to Azure or your choice of cloud. Because you can simply, you're switching your source and sinks, and your fundamental pipeline code is not polluted by a particular source or a particular sink. There is a slight difference in the way which I'm told the portability framework is going to change, but at the moment there's a slight difference in the way Dataflow deploys the job. So when you use Dataflow to deploy the job, if you have got n number of jar files, they get transmitted to GCS into a staging area, and then the Dataflow job is launched from this staging area in GCS. When you're doing this in the open source Flink platform, you have to construct a Uber jar with all those jars embedded inside that Uber jar, and that is what you deploy to the job manager, which then distributes it to the various task managers. So construction-wise, there's a slight nuance difference between doing this on Google Cloud versus Flink. But like I said, apparently that difference is disappearing in the future. So there's a little bit in these slides about the construction of Uber jars and all the rest of it, which I'm not going to dwell upon. This is what we did. We use open source Quantlib to price 2 million plain vanilla monocurrency interest rate swaps and 100,000 Bermudan swaptions. There were interest rate curves which were built with 3 distinct instruments: forward rate agreements, or FRAs as they're called, bond futures, and plain vanilla swap instruments. These were in 12 currencies and 2 indices. So we used both LIBOR and OIS indices. So there were a total of 72 interest rate curves, which was the market data. And the idea was to price an interest rate swap. If you don't understand all of this, it's an instrument that needs some market data for some processing, right? So there's no point in splitting hairs over this one. The results, as I said, was quite curious. We find that a lot of the institutions, especially in financial services, are severely addicted to XML. So we had a process where we had to benchmark XML and JNI and its behavior between Flink and Dataflow. And we found that Dataflow was, it didn't make that much of a difference for Dataflow to shuffle large XML objects through GCS. It just is fairly phenomenal in shuffling this amount of data. And so there was a qualitative difference in performance when you use XML JNI between Flink as the runner and Dataflow as the runner. And the amber, so I'm referring to the diagram on the top left corner. And the amber one obviously is Flink, and the blue piece is Dataflow. There was a marked difference. Now, curiously, when you switch from a JNI-based exchange of data to a direct call, which is via that temp space I was talking about, where you write the protobuf inside the container, the C++ picks it up and then writes the results back to that /temp in the container. The surprising thing was Flink inside the premises where our networks are not as good as Google's networks actually started to perform much better than Google Dataflow. So we started to get results where Flink as a runner begins to now compete extremely well with Google, which means that what is so exciting about this is that it gives us an opportunity to reproduce Dataflow behavior inside the institution, make sure that the libraries work, make sure that all the operational processes are compliant. The one thing I forgot to mention here is that when we make this external call, at this point, when we make this external call, what we do is we send a bundle of trades. So, for example, we would send a bundle of 10 trades to the C++ process. If there's an exception, we'd like the bundle to be unbundled and a secondary pipeline to try if it can recover those trades. This is fairly critical, or if you can't recover those trades, you dead letter pattern it. The reason this is critical is if a trader is taking a position in the market, they need to know whether you have actually priced the entire portfolio. They would not like to take a position in the market on an incomplete portfolio. So they'd like to know how many trades have errored. So if you're doing 10,000 trades in that portfolio, if 20 trades have errored, they would still like to know what is the exact state of the book, i.e. 9,980 trades have succeeded, 20 have failed. It'll be passed on to the quants to go and try and examine why those failures occurred. So this external call, this dead letter patterning that is available through this external call, all those kinds of issues of debugging your quant code can be done inside the bank before you move all this stuff to the cloud, because debugging all these things in the cloud is a little bit more difficult than if it were on your desktop under your desk. That was the most important takeaway we found out with using protobuf and C++ with Flink. So to me, that just gives us this opportunity to be cloud ready before we actually move to the cloud, de-risk the whole process, and makes Flink quite a critical part of this thing. I think I'm going to stop there and leave a few extra minutes for questions.
Yeah, we have a couple of minutes for a couple of questions. Do we have any questions? So if not, let's move on to the break. Let's thank once again the speaker for his talk, and see you in 10 minutes.
Thank you.